So you hear me well? Yeah, I think so. So my name is Nikita. I work at JetBrains on multiple projects related to concurrent programming. I work in the Kotlin team. I lead a framework for testing concurrency on JVM. I periodically do some research activities. So I'm somewhere in the middle between the academia and the industry. And today, I would like to share a part of this journey of mine. Today, we are going to talk about channels. But before we begin, I would like to learn a little bit about you. So has anyone in this room used channels when programming with the Kotlin Coroutines? Oh, nice. So I see some hands here. Thank you. Those who didn't raise a hand, I think you might say, we don't need channels. We don't use them. We have a more high-level API, such as Flow. And you are right. In most cases, you don't need channels. You often write code similar to this one. You create a flow, specify how to build it, to how to collect the data, and then this flow lazily builds the data and processes it. But, so who has ever used Flow? Oh, nice, thanks. So I'm happy to see that Flow is getting prominent. And, okay, we are using Flow, but let's slightly change the code. So usually we read data in the I/O dispatcher. And let's assume we create this flow and collect it using the UI dispatcher. But since flow is sequential, this code is going to fail. You cannot build it and collect it in different dispatchers. You cannot do it concurrently. The flow is sequential. And to fix this code, you need to use the channel flow builder, which utilizes channel to transfer the data from the coroutine that builds this flow to the coroutine that collects it. In this case, even though you don't use channels directly, you use them implicitly. Okay, another example. You have two flows, and you want to merge them. In Kotlin Coroutines, we have a dedicated function for that. But how is this merge function implemented? Let's take a look. When we run merge, it will create a channel flow and launch two coroutines. These two coroutines will collect the data from the source flows and send them to this shared channel. That's how the merge operator is implemented. It uses a channel under the hood. All right, the last example. You don't use flow, you don't use channels. You just want to integrate with another reactive framework, such as RxJava. You have, for example, an observable source instance and you need to collect all the elements. Again, to do that, we launch a coroutine, equip it with the channel, and transfer all these elements to this channel to consume them afterwards. So channels are everywhere when programming with Kotlin Coroutines. You might not use them directly, but you likely use them indirectly by using more high-level API, by using another framework. Channels are everywhere when you use coroutines. So this is the key communication primitive in coroutines. And we are going to discuss how the channels work under the hood. And you might ask, hey, why should I know all these internals? I don't care. And you shouldn't. The Kotlin team does its best for you not to care about how things are implemented internally. We provide more high-level APIs such as Flow. We try to think about your business logic so you can express it with this API. But yet, periodically, you might face some performance or memory issues, even not related to coroutines. But when you face these issues, understanding how the core primitives work internally might help you with the investigation. So in some sense, when you program with coroutines, knowing how channels work is similar to knowing how hash tables work. You don't use this knowledge most of the time, but sometimes you need to know that. So today, in the next 40 minutes, we're going to discuss why we need channels in the first place. We will discuss the Rendezvous channel semantics and how Rendezvous channels are implemented from the high level. And then we will expand this knowledge to the buffered channels. Let's begin. But let's also forget about channels for a moment. Let's say we have multiple coroutines that produce data and multiple coroutines that consume data. So this is kind of a standard producer-consumer scenario we usually have when in any business application. And these producers and consumers need to communicate some way. How can they do that? Without coroutines, without channels, the most straightforward choice would be a queue. That's what pops up immediately, right? The only nuance is that this queue should be concurrent queue, as producers and consumers can be run in parallel. So in this case, when you have a queue, producers would get some data, for example, read this data, and set it into the queue. At the same time, consumers would run in an infinite loop trying to extract the first element from the queue and process it. Restarting of the queue is empty. Well, do you see any problem here? So, first of all, consumers eat a lot of CPU time when the queue is empty, right? So it actually checks whether there is an element starting over and over and over. So it performs some useless work. And at the same time, consumers might be unable to manage the current workload. And in this case, producers add elements faster than consumers can process them, which will lead to growing this queue out of control, and the application will fail with out-of-memory error. So how can we avoid producers growing the queue out of control and consumers not spending time checking the empty queue? And for that, we need a channel instead of a queue. So this is how we create a channel in Kotlin Coroutines. You just say, OK, I need a channel to transfer the data. And with channels, we have not enqueue and dequeue, but send and receive functions. And when we call receive, and this channel is empty, so there is no data, this receive suspense until new elements appear. At the same time, when you call send, and there is no consumer that can process this element, this send also suspends. So the channel doesn't grow out of control. So this send will wait until there is one who can receive the data. This is the default channel semantics when you create a new channel in Kotlin Coroutines. This channel is called a Rendezvous channel. So let's consider an example to discuss the semantics. Here we have two producers and one consumer that will process the data. And these producers and consumer communicate via a Rendezvous channel, which is initially empty. And these producers and the consumer work in parallel. We need a way to illustrate the current state of each of these producer and consumer actors, and that's where Kotlin will help us. Kotlin will help us to illustrate where we are now for each producer and consumer. So let's say the execution starts with the consumer, which calls receive. Since the channel is empty, this receive call suspends, so the consumer's Kotlin goes into the queue and suspends. So drinking a cocktail here. After that, the first producer starts, it reads the data and is about to send it to the channel. So when it calls send, it comes to the channel and notices that there is a waiting consumer. So it makes a rendezvous with this consumer. That's why the channel is called rendezvous channel. So it means the waiting consumer transfers the data to this consumer and resumes it. So this consumer is now resumed and is ready to process the element. And the first producer also transfers the element and finishes. But if now the second producer starts, it reads the data and sends it to the channel. And no receiver is waiting for this data at this moment, you see? So this send call must suspend. This prevents the producer from progressing and potentially growing the channel out of control. And later on, the consumer continues the execution. It processes the data, then it starts over, calls receive, and comes to the channel, meets this producer, makes a rendezvous, gets the data, resumes this producer, so the producer finishes, the consumer goes to process the data, and when starting over, it comes to the empty channel and suspends. So this is how the rendezvous channel works. Okay, so I believe the semantics is clear now. So here's the question. How to implement a rendezvous channel? All right, to make a proper implementation, you need to write some requirements. First of all, we need this channel to be efficient on a single thread for cloud, so with no contention. Second, we want not to spend too much memory on the data structure itself compared to the memory we need to store the element references. So we want the metadata to be as little as possible. And finally, it would be great if this channel scales under high load. So the more coroutines and threads we have in this producer-consumer scenario, the faster our system works. So with these requirements in mind, we are going to build a rendezvous channel algorithm. So how are we going to do that? So remember, channels remind queues. So it would be intuitive to find a suitable concurrent queue algorithm design and then adapt it for the rendezvous channel semantics. That's what we are going to do now. The most straightforward way to implement a concurrent queue would be to use a standard sequential queue and protect the operations with the global lock. So here's simple code. We have a sequential queue, we have int and lock, we protect the operations. And let's see how this approach works in practice. So here's the multi-producer, multi-consumer benchmark. Half of the threads send elements to the queue, half of the threads receive these elements. And we measure the throughput of the system. So the higher the number, the better. To make the workload more realistic, we also perform some additional work before sending an element and after retrieving one. On the sequential workload, this extra work counts for more than 90% of the execution. So it's quite a realistic workload. And here we observe that the throughput increases with 2 and then with 4 threads, but then it degrades and it reaches a plateau. And the reason is that, besides a huge amount of additional work, the synchronization costs become so high so that this parallelism doesn't help at all. So let's summarize. What is good is that it's fast on a single thread workload, there is no overhead, at the same time it's memory efficient, doesn't produce a lot of garbage because we use sequential efficient queue under the hood. However, this approach doesn't scale at all. We increase the number of threads, and sometimes it gets even worse. Okay, that means that we need to find an alternative, a more scalable approach. In the standard Java library, there is a non-blocking, potentially more scalable concurrent linked queue data structure. This is an implementation of the famous Michael's code concurrent queue algorithm. And internally it maintains a linked list storing elements in these list nodes. That's when you need to add a new item. You create a new node object and link it to the list. And each node contains a 4-byte reference to the element and a reference to the next node. But remember, we want our resulting Rendezvous channel algorithm to be memory friendly, to use as little additional memory as possible. So let's take a look at how much memory we spent here to store a 4-byte reference to one element. So including the object header and the required alignment gap, we spent 32 bytes to store only a 4-byte reference. So that's quite an overhead, isn't it? And apart from that, the linked list design typically results in more cache misses when iterating over it. So let's take a look at the results also. The same benchmark, half of the threads send data, half of them receive it, and we measure the system throughput. And here we see that concurrent linked queue is significantly more scalable. It degrades less on high number of threads and it scales better, but it still reaches a plateau. And here we see a big room of improvement. Right here on this graph, we see a lot of space. So maybe we can try to find a better approach. But let's analyze this one first. So the queue is generally fast on single thread workload, but might induce more cache misses. It's definitely neither memory nor receive friendly because you have this linked list data structure, you have a lot of memory overhead, but it's pretty scalable, as we discussed with the room of improvement. So overall, the design doesn't look perfect for our Rendezvous channel. So is there a better design? And apparently there is one. So there are some papers explaining how modern concurrent queues work. And while these papers differ in details, all these algorithms share the same high-level design. And we are going to discuss the high-level design. The idea is to store queue elements in conceptually infinite array and maintain 2 atomic counters indicating the next slot for enqueue and dequeue operations. So dequeue operation, it first increments enqueue index, thus reserving a slot for installing the element. Then it goes to this slot and installs the element. And the dequeue operation is symmetric. It increments atomically dequeue index, reserves the slot to retrieve the element, goes into this slot and retrieves it. So let's take a look. enqueue starts with an atomic increment, and then installs the element. And then here's the element in the first slot. And when deque comes, it increments deque index, goes to the slot, and extracts A, and finishes. Of course, this design is simplified. We don't even check whether the queue is empty in the deque implementation. But it doesn't matter. The high-level idea remains the same. And I want you to understand the high-level idea. I want you to gain the intuition of how things work internally. And the only thing that is left for this intuition is how to build this infinite array, because we don't have such a data structure in reality. All right, here is a trick. We don't need an infinite array. We need only those cells that are between deque index and enqueue index. Everything on the left or on the right, we don't need it. So let's then split this infinite array into fixed size segments, which form a list, and maintain only those segments that are in our range. So when we need a new slot that is not here, we add a segment. When we don't need the segment anymore, we allow the garbage collector to collect this segment. So we reuse the memory. And here's how this segment is implemented. So we have some IDs in this segment to understand where which segment we need and which slot in the segment we need. By knowing the global enqueue index, for example, we know the segment ID, because we know the segment size, and we know which slot in this segment we need. So we have an array of cells in each segment and a reference to the next counter. So it looks much more memory friendly, right? Because we still have this overhead as with nodes, but we can store many, many cells in the same segment. And let's take a look how this approach works in practice. And it now really scales with increasing the number of threads. So there was indeed a room of improvement. Yes, it might become slightly less efficient under very high load, but it's still 4 times faster than all the alternatives. And to summarize, so this queue design is fast on single thread workload, it scales great, it's memory friendly, it's garbage collector friendly, it produces not many objects, so it's a very good queue design. So let's use this design for a Rendezvous channel. In queue, we have enqueue and deque operations, but with channels, we have send and receive ones. So here we have send index and receive index, but the logic remains very similar. Send starts with the incrementing send index, and then it goes to the reserved array slot. Receive starts with incrementing receive index and comes to its slot. So for example here, receive starts, it increments receive index, then it goes to the first slot, just reserved, and since there is no data in this channel, there is no data in this slot, it suspends. And now when send comes, it also increments the index first, it comes to the first cell. It notices that there is a receiver waiting for an element, so it makes a rendezvous with this receiver, resumes it, passes the element, so this receive can finish, and it finishes, and this send also transfers the element and can finish. But let's take a look what happens when send starts first. So send increments the send index again. It goes to the second cell, and no one is waiting for this send, so it suspends. And then when receive comes, it again increments the index. It goes to the cell. It notices that there is a sender waiting for a receiver. So it grabs the element, resumes the sender, and the sender finishes, and this receive call also got the element, extracted the element, and it also finishes. So that's how the Rendezvous channel works in Kotlin Coroutines. But let's try to take a look from a different perspective. So send, receive, they all start with reserving the index. And after that, they update the array cell. So initially, the cell is in the empty state. It's null. Then when a sender comes or receiver comes, since the cell is empty, no one is waiting for this sender or receiver. So in this case, if the sender comes, it suspends in the cell. If receiver comes, it suspends in the cell. But after that, when the opposite request comes, it resumes the operation, making a rendezvous with it, and they both finish. So this is how we change the cell state internally. And you remember, we still have this infinite array, and we need to emulate it somehow. And as for the queues, we can use the same linked list of segments to implement this infinite array data structure. So let's take a look at some results. So I was working on redesigning channels in Kotlin Coroutines, and the implementation we had before that, it was closer to the concurrent linked queue by design, so it also stored elements in nodes, which form a linked list, but a little bit more complex linked list because the data structure semantics is more complex than a queue one. And after we implemented these modern channels, here we have the same benchmark. Half of the coroutines, we have 10,000 coroutines as far as I remember here. Half of the coroutines send the data, half of the coroutines receive this data, and we change the number of dispatcher threads here to evaluate their scalability, to measure performance. We see that this channel scales much, much better. So it's sometimes 4 times or 3 times faster than the old implementation, produces less garbage. So it works pretty good. So it was a big improvement in Kotlin Coroutines. And besides that, when we don't have a lot of additional work, if we try to measure the channel's performance only on the sequential workload, we'll also see some improvement. These new channels are 20% faster than the old ones. Okay, so that's how the Rendezvous channels work under the hood, and that's how they work in practice. But let's go back to our producer-consumer scenario. So we now utilize the Rendezvous channel to transfer the data. Let's take a closer look. So when we send data, and no one is waiting for this data, we always suspend. We need this because we don't want this channel to grow out of control. But can there be a better design for that? Do we always need to suspend? What I would prefer is to have some buffer which I can fill with these elements and suspending only when this buffer is full. And that's what we have in Kotlin Coroutines. We have a buffer channel. So when you create a channel, you can specify the channel capacity. And for example, here, by specifying capacity key, you can send first key elements without suspension, and the next send call will suspend as the channel is full. So this channel is usually called buffer channel. So let's take a deeper look at the semantics of the buffer channel. So here we have the same, two producers, one consumer, and a channel of capacity 1. So we have buffer for one element. For example, the first producer starts. It reads the data and sends it to the channel. The buffer is empty, the channel is empty, so we can simply add this data 1 to the channel and finish. We don't need to suspend because we have some space in the buffer. But if another consumer, another producer comes now, then it notices that the buffer is already full. So it needs to wait until free space appears in the buffer, and this producer suspends. So now we switch our execution to the consumer. It calls receive to extract the first element. It comes to the channel, and it finds an element in the buffer, so it extracts it. And now the buffer is empty, right? The buffer is empty, and there is a waiting producer. So this consumer, this receive call, it also resumes the waiting producer, moving its element into the buffer. So this producer can finish, and this consumer just finished the receive call and processes the data from the first producer. And when it starts over on the next iteration, it calls receive again, it comes to the channel again, it finds the data 2 element in the buffer, it extracts it, and there is no one waiting on the channel, so there is no one to be resumed. And this consumer simply processes the data. And when it comes to the empty channel, then the logic is similar to the rendezvous channel. There is no data. This receive call should suspend until new data appear. So this consumer suspends. This is the semantics of the buffered channel. So how can we implement it? It's significantly more complicated semantics, actually. But we can apply the same design. The only difference is that now we need to have this buffer. But instead of having an external buffer, let's have an imaginary buffer. Let's say that in this infinite array, we know where this buffer ends. So for that, we add an additional counter that indicates the first cell that is not a part of the buffer. And the rest remains the same. But how does this semantics, this change affects the algorithm design? Well, so with the rendezvous channel, we have a pretty simple cell life cycle, right? So it's very straightforward. And then we apply a technique which is well known in the academia, actually. So when you have something simple, you need to make something complex, you use this. And this is the cell life cycle for buffered channels. We are not going to discuss it. It gets a little bit more tricky, not only because the buffered semantics is more complicated, yes, it is, but also because we need to suppose some coding cases that we didn't discuss, like that while suspending, coroutines can get cancelled. So, for example, you have receive call and the coroutine gets cancelled, so we need to deregister this receive from the channel. And when you mix these cancellation semantics, the buffered semantics, you get this. So if you are interested in the details, we have a paper that describes it from different points of view. We also have source code that is very well documented. But please, first, if you want to dive into this, first read the paper, then the source code. OK, so with the buffered channels, the high-level idea is the same. We have this infinite array, we have some counters, and we do some weird synchronization in the cell. But you remember this picture, right? So it's really complex. And usually, when it gets more complex, it gets slower. So is this approach fast? Let's take a look. So let's compare with the previous channel implementation. So here is the channel of buffer channel of capacity 64, and the same multi-producer, multi-consumer benchmark. And if we observe that this new channel, it scales very, very well. It scales similarly to the modern queues, despite the fact that the semantics is significantly more complicated. And it also means that now if you use channels under high load, you don't really need to care about performance. You can be sure that it won't degrade. You can be sure that we have a very strong communication, a very efficient and scalable one. And this applies not only to Rendezvous and buffer channels. Yes, these are the most important ones. But we have a big family of channels. We also have unlimited channels, channels of unlimited capacity. We have conflated channels. We have a mix of conflated and buffered channels. And all of them share this design. So what we've learned today. First of all, that even if you don't use channels directly, you likely use them indirectly through another API or frameworks. We've discussed the Rendezvous and buffer channel semantics and their high-level implementation design. And I also used Kodi a lot, so I hope you noticed that Kodi is very cute. And if you are interested in all these implementation details in Kotlin Coroutines, in exactly 1 month, we are going to give a series of talks on different algorithms, internal algorithms in Kotlin Coroutines. It's going to be here in Copenhagen at PLDI conference. So we're going to talk about the scheduler, about channels, about mutex semaphore implementation, and about framework we use to test all this concurrent code. So if you're interested, I will be happy to see you there. And thank you very much to be here, and don't forget to vote for the talks. So we have some time for questions.
Hey, test, test, test. Okay, perfect. Thanks for your talk. My question is, what if you have multiple producers that are suspended and then someone receives? Which producers picked, basically?
So when you have multiple producers that are suspended, then the consumer will pick the first one. So all the requests are processed in the first in, first out order, like in the queue.
Okay, thanks.
So here's another question here, I see. 2 questions.
Thanks a lot for your talk.
Excuse me, can we increase the volume of the microphones?
I have a question about this one graph that you showed about the efficiency depending on or for different numbers of threads. And I wanted to ask you, do you know for a higher number of threads how this scales, this algorithm?
Do I know how it scales for high number of threads? Yes, I do. It scales very similarly. So I just tested it on an AWS instance that had only 64 cores. I didn't use more cores because when you use Kotlin Coroutines, you usually limit the number of dispatcher threads to the number of cores because it doesn't make sense to have more threads than that. But if you test it with I tested with 192 threads on the corresponding machine. The trend was very similar.
I have one question. In the case that there are multiple
Where are you? I don't see you.
here, sorry.
Aha, I see. Thanks.
A little hidden here, but in the case there are multiple producers, is it always at the time of sending the information that they are going to be resumed? Or it's like kind of random, like I have four producers and then like it's 1, 3, 4, 2, for example. It will be executed in the same order and...
Sorry, I didn't get the question. Can you repeat it?
Oh, in the same order that they post in the channel, then they will be resumed.
So here's some of the part of the discussions very funny.
Sorry.
Quick question. I wanted to ask, how do you choose the segment size? Because the way I understood it, basically a linked queue would be like the same modern queue, but with a segment size of 1, essentially. So how do you decide, like, how do you decide the size so that it's not so little that you have new pointers, too many pointers, and it's not so big that you actually don't use, you know, the free slots, the allocation of the memory?
Okay, that's a good question. Thanks. So I don't have a good answer for you. You just pick some size that is intuitively good.
Okay.
So like, it's a standard library. So you can't make it too high. You can't say that the segment size is 1,000. It would be too much. But if you choose it like 4, it's too small because you have a lot of metadata. So you choose something in between. And as far as I remember, we store 32 elements in each segment, and it works good. Not really. But usually it's 16, 32, or 64. Then it's too big, and less than 16 is too small. So somewhere in the middle.
Yeah. One comment is that if you can use atomic foo, maybe it's time to make it stable in coroutines quite a lot. But the question is, or maybe, I think it's quite problematic that channel flow by default has a buffer of size 64 and it's suspending when the size is reached. It is problematic in many cases, especially when we are wrapping over some watchers or listeners, because since we mostly use try send blocking there, it's literally blocking the listener, and the consequences of that are not clear. And this is not configurable. So are you planning to make it configurable, the size of the default buffer, or maybe considering changing that to infinite, which would probably be more intuitive as a default value?
So thanks for this design question. So what I would ask from my side is to create a GitHub issue, explain your use case, because we have a team who works on designing the API. Me personally is not really involved in this. Sorry, maybe I'm not the right person to talk about this, but I can find the guy who can help you with that. But anyway, if you have an issue on GitHub, then we can take a closer look. We can understand your case better and try to help you.
Okay, thank you.
So I think the last question, we have 40 seconds.
So I was curious about whether you have any information about how a regular Java blocking queue on virtual threads would work against these.
Okay, so in Java, they also have for data structures similar to channel. So it's indeed, it's a blocking queue, it's the buffer channel. What they do is that they use a global log for synchronization. So it doesn't scale at all. So if you want to have proper channels, use Kotlin Coroutines. So I think we ran out of time. So Thank you very much, and if you want to discuss something, I will be here.